Look up at the night sky. What do you see? Stars, galaxies, the shimmering glow of distant cosmic wonders. But here's the truth. Everything visible to us, every spiral arm of every galaxy, every shimmering speck of light accounts for less than 20% of the universe's total mass. The rest, an invisible, enigmatic force weaving through the cosmos like a ghostly hand shaping reality itself. This is dark matter, the universe's greatest unsolved mystery, and its influence is everywhere. Vast halos of this elusive substance envelop galaxies, bending space, guiding the birth of stars, and sculpting the very fabric of the cosmos, yet we've never seen it directly. Imagine an architect building a cathedral in complete darkness, their blueprints written in a language we're only beginning to decipher. That's what it's like to study dark matter halos. These invisible structures stretch millions of light years across, binding galaxies together with gravitational threads we can't see but know must exist. Without them, the universe as we know it would fly apart, stars scattering like sand in the wind. And yet, despite their colossal importance, dark matter halos defy every tool we've built to detect them. They don't emit light, reflect it, or interact with ordinary matter in any way except through gravity, a cosmic whisper in the dark. Today, we're unraveling 25 of the most astonishing mysteries hidden within these shadowy giants. How do they dictate the fate of galaxies? Why do they cluster in ways that defy our models? What strange particles might lurk within them, waiting to rewrite the laws of physics? From the eerie missing satellite problem to the baffling dance of colliding galaxy clusters, each discovery peels back another layer of this cosmic enigma. So join me on a journey into the invisible architecture of the universe where every answer leads to deeper questions, and the greatest secrets are written in the darkness between the stars. The truth is out there, and it's far stranger than we've ever imagined. Picture holding a massive, invisible bowl made of pure gravity, one so vast it could cradle an entire galaxy inside it. That's the strange reality of a dark matter halo. These enigmatic structures don't just sit idly in space, they actively shape it, warping the paths of stars and galaxies with their unseen grip. Think of them as the universe's hidden architects sketching blueprints in gravity alone. Without them, galaxies like our Milky Way would spin apart, their stars flung into the void like marbles escaping a broken string. But how do we study something we can't see? Here's where nature hands us a cosmic magnifying glass, gravitational lensing. When light from a distant galaxy passes near a dark matter halo, the halo's immense gravity bends that light, distorting the galaxy's image like a funhouse mirror. Astronomers analyze these warped images stretched into arcs or smeared into ghostly rings. To map the halo's mass and structure, it's detective work on a galactic scale, where even the absence of light reveals the presence of shadow. Take the famous Bullet Cluster, for example. When two galaxy clusters collided, their dark matter halos sailed right through each other, leaving the visible gas behind like smoke in the wind. By observing how the halo's gravity bent background light, scientists confirmed dark matter's existence in one of the most striking proofs ever captured. Yet for every revelation like this, a deeper mystery emerges. Why do these halos seem to have a fluffy edge, fading gradually rather than ending abruptly? And how do they manage to influence galaxies billions of years after forming? The more we learn, the clearer it becomes. Dark matter halos aren't just passive backdrops. They're dynamic, evolving entities, their gravitational fingers tugging at the universe in ways we're only beginning to understand. And with each new lensing observation or supercomputer simulation, we catch another fleeting glimpse of the invisible framework holding everything together. One of cosmology's most persistent puzzles lies in the gaps between what our models predict and what we actually see specifically. The eerie shortage of dwarf galaxies swarming around giants like the Milky Way. According to our best simulations, dark matter halos should be littered with hundreds of these tiny satellite galaxies, each a flickering candle in the cosmic dark. Yet when we look, only a few dozen appear. It's as if someone erased half the stars from the sky and left no explanation. Scientists call this the missing satellite problem, and it's been haunting astronomers for decades. So where did all those galaxies go? One tantalizing possibility is that dark matter isn't as sluggish as we once thought. The traditional cold dark matter model assumes these particles move slowly, clumping easily into vast halos and their smaller satellite blobs. But what if some dark matter is warm, zipping through space just fast enough to resist forming as many dwarf galaxies? Simulations with warm dark matter do show fewer satellites aligning better with observations. Yet even this theory can't fully explain the gap. Then there's the observational hurdle. Maybe the missing satellites aren't missing at all, just hiding. Dwarf galaxies are notoriously faint, their stars scattered like grains of sand against the blackness. Some could be cloaked behind clouds of interstellar dust, or their stars so sparse they blur into the background glow of the Milky Way. Recent discoveries of ultra-faint dwarfs, some with just a few hundred stars, suggest we're finally peeling back the veil, but the numbers still don't add up. Another twist, perhaps these dwarfs existed once, only to be torn apart by the Milky Way's gravity over billions of years, their stars smeared into ghostly streams like cosmic breadcrumbs. Surveys have already found remnants of such cannibalized galaxies in our own halo, hinting at a violent past, but even accounting for these disruptions, the discrepancy lingers. The missing satellite problem isn't just a counting exercise. It's a direct challenge to our understanding of dark matter itself. Each potential solution, from warm particles to hidden galaxies, forces us to rethink the invisible scaffolding of the universe. And until we crack it, this cosmic game of hide and seek reminds us just how much we've yet to learn about the shadows shaping our night sky. Imagine building a universe inside a supercomputer, painting galaxies into existence, wiring the laws of physics, and hitting start. Your simulation hums to life, crafting vast dark matter halos exactly as predicted, until something bizarre appears. A handful of these halos grow so massive they should cradle galaxies brighter than the Milky Way. Yet when you peer into the real night sky, empty, just cosmic voids where dazzling cities of stars ought to be. This glaring mismatch between simulation and reality has a name, the too big to fail problem, and it's shaking our understanding of dark matter to its core. Here's the contradiction in action. In ultra-precise models like the Millennium simulation, certain dark matter halos balloon to staggering sizes, some with 50 times the mass of the Milky Way's halo. Their gravity should pull in enough gas and dust to birth entire galactic superpowers. Instead, when we scan their real-world locations, we find only dim, wispy dwarf galaxies or nothing at all. It's like spotting footprints of a giant, but the giant itself is missing. So where did these phantom giants go? One leading theory points to the violent tantrums of young galaxies. Picture a fledgling galaxy forming inside one of these oversized halos. As its first stars ignite, they unleash torrents of radiation and supernova explosions, cosmic feedback that blasts away nearby gas before it can form more stars. Over time, this self-sabotage could leave the halo starved of material, producing only a faint shadow of the galaxy it should have been. Simulations that include these feedback effects do show fewer ultra-bright galaxies, nudging predictions closer to reality. But the match still isn't perfect. Some halos remain stubbornly overlit, while others are too dark. Then there's the dark matter angle. What if the particles themselves behave differently than we assume? Most models treat dark matter as cold, slow-moving and clumpy. But if some of it were slightly warmer, with particles zipping around faster, they might resist piling up as densely in halos. Less density means weaker gravity, which could explain why these halos failed to attract enough gas to form bright galaxies. It's a subtle tweak, but when researchers ran simulations with this adjusted dark matter recipe, the number of too big halos dropped dramatically. Yet even these elegant solutions can't fully close the case. Take the Dragonfly telescope's recent discovery of ultra-diffuse galaxies, a faint, sprawling objects floating in exactly the kind of massive halos the problem highlights. These ghostly galaxies shouldn't exist under either feedback or warm dark matter scenarios, yet there they are, glowing softly in the dark. It's as if the universe is teasing us with exceptions to every rule we propose. The too big to fail problem isn't just academic. It forces us to confront gaps in our knowledge that could redefine dark matter itself. Whether the answer lies in galactic feedback, exotic particles, or something entirely unforeseen, one truth is clear: the cosmos thrives on throwing us curveballs. And with each paradox we untangle, the invisible hand shaping our universe becomes just slightly less mysterious. If dark matter halos were cities, their downtown cores would be the most puzzling districts of all. Simulations have long predicted these centers should be densely packed peaks of gravitational intensity where dark matter particles crowd together like commuters in a cosmic subway station. Yet when astronomers measure the actual rotation speeds of stars and gas in galaxy cores, the data tells a different story. Instead of a sharp spike in density, many galaxies appear to have soft, almost fluffy centers, like a cloud rather than a spike. This mismatch between theory and reality is the heart of the cusp core controversy, and it's forcing scientists to question whether dark matter plays by the rules we've written for it. The conflict starts with cold dark matter theory, the foundation of most modern simulations. In these models, dark matter is cold, slow-moving, and gravitationally sticky, piling up in halos with steep density peaks at their cores. Picture a ball of yarn wound tight at the center, the strands growing denser as you spiral inward. But when astronomers study dwarf galaxies, especially faint ones like Draco or Fornax, they find stars drifting lazily around these cores as if the gravitational pull were far weaker than simulations predict. It's like expecting a whirlpool and finding instead a gently stirred cup of tea. So what's smoothing out these supposed cusps? One provocative idea is that dark matter isn't entirely dark after all, at least not to itself. Perhaps dark matter particles can interact with each other through some unknown force, bumping and scattering like billiard balls in the crowded core. These collisions could redistribute energy, puffing up the center into a shallower profile. Think of it like a crowded dance floor. If dancers keep bumping into each other, they'll naturally spread out rather than clumping in one spot. Simulations of this self-interacting dark matter do show cores that better match observations, but there's a catch. If dark matter interacts too strongly, it would erase other halo features we know exist, like the sharp edges seen in galaxy clusters. Then there's the wild card, ordinary matter. Stars and gas might seem like bit players in a dark matter-dominated universe, but their influence could be dramatic. Supernova explosions, stellar winds, and the churning of galactic disks could inject enough energy to literally push dark matter around, smoothing the core from the inside out. Picture blowing air into a pile of sand. The grains shift, creating a shallower mound. Some simulations incorporating these baryonic feedback effects produce cores that align beautifully with observations. But critics argue this requires fine-tuning, as if the universe dialed in the exact amount of stellar fireworks needed to fix the problem without overdoing it. The debate gets even murkier when you consider galaxies that stubbornly refuse to fit either narrative. Take the ultra-diffuse galaxy Dragonfly 44, a ghostly smudge of stars floating in a massive dark matter halo. Its core is strangely diffuse, yet it lacks the star-forming frenzy needed to explain this through baryonic physics. Meanwhile, some galaxy clusters still show hints of dense cusps, as if dark matter's behavior changes depending on the cosmic neighborhood. This isn't just academic squabbling. The cusp-core controversy cuts to the heart of how we understand dark matter's fundamental nature. If cores are smoothed by self-interactions, we might be on the verge of discovering a whole new physics beyond gravity. If baryons are the culprits, it means ordinary matter plays a far more dynamic role in shaping galaxies than we ever imagined. And if neither answer fully fits, well, that's when things get really interesting. The universe, it seems, loves handing us puzzles where every solution opens 3 new questions. At the heart of the dark matter mystery lies a fundamental question: is this invisible substance sluggish or swift? The answer could reshape everything we know about galaxy formation. Cold dark matter, the reigning champion of cosmological models, moves slowly, so slowly that in the early universe its particles clumped together easily under gravity's pull, forming vast halos with intricate substructures. These halos became the gravitational scaffolding for galaxies, their dense cores acting like anchors for swirling disks of stars. Picture syrup poured onto a pancake, pooling thickly in the center. That's cold dark matter, settling into the cosmic landscape with gravitational glue. But cracks in this picture emerged when telescopes revealed galaxies with puzzling features. Missing satellites, oddly fluffy cores, and dwarf galaxies drifting too far apart. Enter warm dark matter, the challenger. Faster moving, these particles would have zipped through the primordial universe like whispers in the wind, resisting tight clumping. The result: halos with smoother edges, fewer satellite galaxies, and central cores less dense than cold dark matter predicts. Think of the difference between packing snow into a tight ball versus tossing a handful of sand. Each leaves a distinct imprint. The implications ripple across cosmic history. Cold dark matter's clumpiness should have birthed galaxies earlier and more abundantly, filling the universe with bright stellar metropolises. Yet some of the oldest, most distant galaxies we've found appear suspiciously mature, as if they formed too quickly for the cold model's timeline. Warm dark matter, with its gentler touch, could explain this by delaying galaxy formation slightly, allowing gas to cool more gradually. But here's the twist: warm dark matter struggles to explain the sprawling web of galaxy clusters we observe today. Its particles, moving too briskly, would have smoothed out the universe's large-scale structure like a cosmic iron, erasing the filamentary networks etched across the sky. Observations haven't settled the debate. Take the bizarre case of the Milky Way's 2 big satellite galaxies. Some, like the Large Magellanic Cloud, are heftier than cold dark matter simulations predict. Warm dark matter could trim their numbers, but then why do we still see a few oversized outliers? Meanwhile, studies of the cosmic microwave background, the afterglow of the Big Bang, lean toward cold dark matter, its fingerprints matching the faint temperature fluctuations nearly perfectly. Perhaps the truth lies somewhere in between. Some theorists propose a mix, mostly cold dark matter with a sprinkle of warmer particles, like blending 2 paints to get the perfect hue. Others suggest dark matter might change behavior over time, cooling as the universe expanded. Then there's the radical idea that dark matter isn't one thing at all, but a family of particles with different speeds and properties, each leaving its mark on the cosmos. The cold versus warm debate isn't just academic, it's a window into the universe's hidden blueprint. Whichever model prevails, or whether an entirely new framework emerges, one thing is certain: the answer will rewrite our understanding of how galaxies live, die, and dance in the dark. Among the cosmic curiosities that challenge our understanding of dark matter, few are as baffling as the ultra-diffuse galaxies, ghostly apparitions of the night sky, stretching as wide as the Milky Way but glowing with only a fraction of its starlight. Take Dragonfly 44, a celestial spectre floating in the Coma cluster. Despite spanning 60,000 light-years, this galaxy emits less than 1% of the light you'd expect from its size. It's as if someone stretched a handful of stars across a canvas the size of a city and called it a galaxy. Yet here's the kicker, its dark matter halo weighs as much as the Milky Way's. How does such a faint wisp of stars anchor itself to something so massive? The answer might rewrite the rules of galactic evolution. Most galaxies follow a predictable pattern. The more stars they have, the more dark matter they're wrapped in. But ultra-diffuse galaxies like Dragonfly 44 flip this logic on its head. Their starlight is so feeble, you'd expect their dark matter halos to be equally puny. Instead, they're gravitational titans in threadbare cloaks. Imagine finding a balloon so light it barely weighs a gram, only to discover it's anchored to an invisible lead weight. That's the paradox these galaxies present. One theory suggests these cosmic ghosts are failed galaxies. Early in the universe, their halos may have gathered enough gas to birth stars, but something went wrong. Perhaps supernova or ravenous black holes blasted away their star-forming fuel too soon, leaving behind a skeletal framework of stars adrift in a still massive halo. Or maybe they formed in unusually quiet cosmic neighborhoods where sparse gas reserves meant they never had a chance to shine brightly. Then there's the dark matter factor. Could the halos themselves be to blame? Some simulations hint that halo spin plays a role. Fast-rotating halos might spread their gas too thin, preventing dense star-forming regions from taking root. Others propose that ultra-diffuse galaxies are the survivors of violent encounters, their outer stars stripped away by collisions, leaving only their dense, dark matter-rich cores intact. But the plot thickens with discoveries like NGC 1052 DF2, a galaxy so lacking in dark matter it shouldn't exist under current models. If ultra-diffuse galaxies can swing from halo-dominated to halo-starved, what does that say about dark matter's role in their formation? Are these galaxies cosmic accidents or signs of a hidden diversity in how dark matter clumps and clings? Every new observation peels back another layer of mystery. The more we study these faint giants, the clearer it becomes. They're not just oddballs. They're critical stress tests for our theories, proving that the relationship between dark matter and starlight is far more complex and far more fascinating than we ever imagined. Deep in the cosmic archives, astronomers have uncovered a paradox that defies everything we thought we knew about galaxy formation halos brimming with dark matter, yet eerily empty of stars. These invisible giants, detected solely by their gravitational fingerprints, loom like ghost ships adrift in the intergalactic void, the most famous example. The dark Milky Way candidate uncovered in the Virgo cluster, a halo with enough mass to rival our own galaxy, but without a single visible star to call its own. How does a gravitational trap so powerful fail to catch even a flicker of starlight? The answer could rewrite our cosmic playbook. One leading theory points to a cosmic starvation diet. For a dark matter halo to birth a galaxy, it needs to pull in vast reservoirs of gas, the raw material for star formation. But in dense environments like galaxy clusters, neighboring giants can act like bullies, stripping away this gas before it has a chance to collapse. Picture a fledgling galaxy trying to gather clouds during a hurricane. The halo's gravity might still hold firm, but without gas to fuel stellar nurseries, it becomes a dark cathedral with no congregation. Then there's the temperature factor. Some halos may reside in regions where the intergalactic gas is simply too hot to settle. Imagine trying to freeze ice cubes in a sauna. The ambient heat keeps molecules buzzing too vigorously to stick together. In these environments, even a massive dark matter halo might fail to cool its gas enough to form stars, leaving it permanently dark. Supporting this, X-ray telescopes have spotted galaxy clusters where the space between galaxies simmers at millions of degrees, creating a hostile zone for star formation. But perhaps the most tantalizing possibility is that these halos aren't entirely barren. Some could harbor failed stars, objects like brown dwarfs or rogue planets, too faint for our telescopes to detect. Others might shelter primordial black holes, relics from the universe's violent infancy. These shadowy occupants could explain the halo's gravity while remaining invisible to conventional surveys. It's like finding footprints in the snow but no sign of the creature that made them. The implications ripple across cosmology. If halos routinely fail to form galaxies, our census of dark matter's influence might be woefully incomplete. Current models suggest the universe contains 50 times more dark matter than visible matter. But if countless halos lurk unseen, that ratio could tilt even further. More profoundly, these dark halos challenge our understanding of feedback, the delicate balance between gravity and energy that dictates whether gas becomes stars or remains forever diffuse. Every undetected halo is a silent witness to processes we're only beginning to grasp. And as telescopes grow more sensitive, who knows what other shadowed giants we'll find, waiting in the dark, rewriting the rules one invisible thread at a time. If you mapped every known satellite galaxy orbiting the Milky Way, you'd expect chaos, a swarm of tiny islands drifting in random directions like bees around a hive. Instead, astronomers found something shockingly orderly. Nearly half of these dwarfs align in a razor-thin plane, a disk-like structure that slices through our galaxy like a cosmic vinyl record. This plane of satellites defies the very foundation of dark matter theory, which predicts halos should host satellites scattered in all directions, not neatly arranged as if placed by an unseen hand. The discovery sent shockwaves through cosmology. Imagine tossing a handful of marbles into the air statistically. They'd land in a messy, uneven spread. But if they somehow landed in a perfect circle, you'd suspect someone tampered with gravity itself. That's the level of anomaly we're dealing with. The Milky Way's satellite plane isn't just slightly clustered. It's improbably flat, stretching over 1 million light-years, yet less than 30,000 light-years thick. Even stranger, many of these dwarfs orbit in sync, moving like dancers in a choreographed routine, rather than the disorganized free-for-all simulations predict. So how did this cosmic conga line form? One radical idea suggests these satellites aren't independent galaxies at all, but survivors of a single ancient collision. Billions of years ago, a smaller galaxy might have slammed into the Milky Way, its stars and dark matter ripped apart by tidal forces. The remnants, now our satellite dwarfs, could have retained their shared motion, frozen in the orbital plane of their progenitor. It's like finding a string of pearls and realizing they were once part of the same broken necklace. Some simulations support this group Unveil scenario, showing disrupted galaxies can leave behind trails of satellites in coherent orbits. But here's the catch: not all the Milky Way satellites fit this plane. A significant fraction still float outside it, suggesting either multiple formation mechanisms at work or that the plane's coherence is a fleeting illusion. Worse, when astronomers spotted similar planes around Andromeda, our galactic neighbor, the alignment was even more pronounced, with nearly 80% of its satellites locked into a disk. If these structures are cosmic coincidences, their recurrence stretches probability to the breaking point. Alternative explanations dive into the nature of dark matter itself. Could the halos hosting these satellites be shaped like squashed soccer balls rather than spheres, funneling dwarfs into preferred orbits? Or might dark matter's gravitational pull interact with visible matter in unexpected ways, herding galaxies into alignment over eons? Some theorists even propose these planes are scars from the universe's infancy, imprints of primordial filaments that funneled gas and dark matter into flat sheets before galaxies formed. Yet every hypothesis comes with trade-offs. The collision scenario struggles to explain why similar planes exist around isolated galaxies with no signs of past encounters. Modified dark matter models risk undermining other pillars of cosmology, like the pristine agreement between simulations and large-scale galaxy clustering. And if primordial conditions seeded these planes, why don't all galaxies display them? The plane of satellites is more than a curiosity. It's a direct challenge to our understanding of how dark matter structures the cosmos. Whether the answer lies in violent galactic histories, unseen dark forces, or flaws in our simulations, one thing is certain: the universe keeps handing us puzzles that refuse to fit neatly into any box. And until we solve this one, the Milky Way's mysterious disk of dwarfs will remain a glaring reminder of how much we've yet to learn about the invisible scaffolding of reality. Astronomers expected the infant universe to be a quiet, sparsely populated place, a cosmic nursery where galaxies took eons to grow from tiny seeds into sprawling metropolises. Then the James Webb Space Telescope turned its infrared eye toward the dawn of time, and the cosmos delivered a shock. There, glowing in the darkness just 500 million years after the Big Bang, were fully formed galaxies, monsters the size of our Milky Way, wrapped in halos of dark matter so massive they shouldn't have existed yet. It's like finding a skyscraper in the middle of the Stone Age. These ancient behemoths, like the jaw-droppingly massive Galaxy Z13, shouldn't be possible under standard dark matter theories. Cold dark matter models predict halos grow slowly, accumulating mass through gravitational mergers over billions of years. Yet here are galaxies 100 times heavier than expected, their dark matter halos apparently assembled in a cosmic blink. How did gravity work overtime to build these titans so soon after the universe's birth? One clue might lie in the primordial soup of the early cosmos. In the first moments after the Big Bang, tiny quantum fluctuations, random ripples in density, could have created ultra-dense patches where dark matter piled up faster than average. Think of these patches as cosmic cheat codes, regions where the rules of slow and steady growth didn't apply. If these overdense seeds existed, simulations show they might have jump-started halo formation, funneling matter into colossal structures ahead of schedule. But there's a catch. Even these turbocharged seeds shouldn't explain the sheer size of JWST galactic giants. That's led some theorists to propose wilder ideas like dark matter cannibalism. Suppose early dark matter wasn't made of just one type of particle, but multiple species with different masses. The heavier particles could have decayed into lighter ones, releasing energy that supercharged halo growth. Picture throwing gasoline on a campfire. Suddenly, the flames leap higher than nature alone would allow. Then there's the dark horse candidate, primordial black holes. If swarms of these ancient black holes littered the young universe, their gravitational heft could have accelerated halo formation, acting as instant scaffolding for galaxies. It's a radical solution, but JWST observations are forcing us to consider possibilities we once dismissed as science fiction. The implications are staggering. If dark matter halos really grew this fast, we might need to rewrite the story of how every galaxy formed. More unsettling, these early monsters challenge the very timeline of cosmic dawn, suggesting the universe got its act together far quicker than we ever dreamed. And with JWST peering even deeper into the past, who knows what other cosmic rule breakers are waiting in the shadows? Dark matter halos aren't just invisible, they're shape-shifters. While we often picture them as perfect spheres, like cosmic soap bubbles suspended in space, the reality is far messier. Some are flattened like pancakes, others stretched into cigar-like filaments, and a few even twisted into lopsided, chaotic blobs. This dizzying variety isn't random. It's a cosmic fingerprint, revealing everything from violent collision histories to the very nature of dark matter itself. Take the halo around the galaxy Centaurus A, a warped, elongated monster that looks like it's been pulled apart by invisible hands. Its strange shape betrays a dramatic past, a brutal merger with another galaxy billions of years ago. When two halos collide, their dark matter doesn't smash together like ordinary matter. Instead, it forms a gravitational tug-of-war, stretching and distorting the halos into odd configurations before settling into a new, often asymmetrical shape. Picture two taffy candies slowly merging in zero gravity, their edges fraying and blending unpredictably. These cosmic train wrecks leave behind halos that are anything but spherical, their forms frozen in time like scars. But mergers aren't the only sculptors at work. The intrinsic properties of dark matter particles might also play a role. Cold dark matter, moving sluggishly through space, tends to clump into rounder halos. Its slow speed lets gravity smooth out irregularities. But if dark matter has even a tiny bit of warmth with particles zipping around faster, they'd resist settling neatly, creating halos that are more oblong or even donut-shaped. It's the difference between pouring syrup, which pools smoothly, and scattering sand, which lands in uneven mounds. Some theorists even suggest certain dark matter particles could interact with each other through unknown forces, creating halos with bizarre, lumpy geometries that defy traditional models. Then there's the cosmic environment itself. Halos floating in crowded galaxy clusters face constant gravitational harassment from neighbors, their shapes stretched and sheared like putty in a toddler's hands. Meanwhile, isolated halos in the cosmic boondocks often retain pristine, near-spherical forms undisturbed for billions of years, the most extreme examples. Prolate halos are structures stretched into needle-thin lines, likely forged in the aftermath of ancient, head-on collisions between galaxy clusters. These cosmic slivers challenge our assumptions about how easily dark matter can be pulled out of equilibrium. The shapes we observe aren't just curiosities, they're breadcrumbs leading back to dark matter's deepest secrets. A spherical halo might hint at a quiet, uneventful life, while a misshapen one could be a billboard advertising past cosmic violence. And if we ever find halos with shapes no simulation can explain, that's when things get really interesting, a sign that dark matter's rulebook might need a rewrite. Every distortion, every asymmetry is a clue waiting to be decoded, and with next-generation telescopes mapping halos in unprecedented detail, we're closer than ever to reading the full story written in these invisible, ever-changing forms. When galaxies collide, chaos reigns, stars scatter, gas clouds ignite, and black holes awaken in a dazzling light show. But hidden beneath this spectacle lies something far stranger. Dark matter halos slipping through the wreckage like silent ghosts untouched by the violence around them. The Bullet Cluster, one of the most studied galactic pileups in the universe, offers the clearest proof of this eerie phenomenon. Here, two galaxy clusters smashed together at millions of miles per hour, and when the cosmic dust settled, their dark matter had done the impossible. It sailed right through the collision, leaving the visible gas behind in a turbulent wake. This decoupling was dark matter's smoking gun. Astronomers mapped the cluster's mass using gravitational lensing, tracing how their gravity warped light from background galaxies. The result, two distinct peaks where the dark matter halos had traveled, completely detached from the glowing gas clouds that should have anchored them. It's as if you shook two snow globes together, only to find the glitter settled in one place while the water pooled somewhere else entirely. This bizarre separation proved dark matter doesn't behave like anything we're familiar with. It barely interacts with itself or ordinary matter, feeling only gravity's faintest tug. But the Bullet Cluster isn't alone. Systems like MAX J0025.4-1222 reveal similar splits, with dark matter halos drifting ahead of their gas like ships leaving a trail of smoke. These collisions act as natural laboratories, exposing properties no telescope could detect otherwise. For instance, the halo's sluggish response to collisions suggests dark matter particles rarely collide, if they interact at all. In some mergers, like Able 520, the halos even seem to stall, lagging behind their galaxies as if fighting invisible friction, yet puzzles remain. Why do some clusters, like El Gordo, show halos clinging closer to their gas? Could dark matter's behavior change depending on a collision's speed or angle? The answer might lie in the particles themselves. If dark matter has even a minuscule ability to interact through some unknown force, those rare particle bumps could subtly alter how halos move during crashes. Alternatively, the gas might not be as passive as we thought. Magnetic fields or turbulence could bind it more tightly to dark matter in certain cases, blurring the clean separation we expect. Every collision paints a new piece of the portrait, and as we discover more of these cosmic wreckage sites, each with its own quirks, one truth becomes clear: dark matter isn't just an inert backdrop. It's a dynamic, if elusive, player in the universe's grand ballet, one that leaves its fingerprints not in light, but in the silent, persistent pull of gravity. Amid the vast cosmic web, where galaxy clusters thread together like glittering strings of pearls, there exist desolate wastelands, regions so empty they're called voids. These are the universe's ghost towns, spanning hundreds of millions of light years with barely a star to break the darkness. Yet even here, dark matter halos lurk, some clinging stubbornly to solitary galaxies, others standing utterly empty. Why do some of these phantom halos remain barren while others become oases for lonely starlight? The answer could rewrite our understanding of how galaxies are born or fail to be. Take the void halo DR7, a gravitational behemoth caught in the middle of nowhere. Its mass could cradle a galaxy like the Milky Way, yet scans reveal only silence, no stars, no gas, not even a wisp of cosmic dust. Meanwhile, its neighbor VOID 32, a similarly isolated halo, hosts a single, flickering galaxy, its stars burning faintly against the abyss. This stark difference defies simple explanation. If both halos formed in the same void environment, why did one attract enough gas to ignite stars while the other languished in darkness? One clue lies in the voids themselves. These regions aren't just empty, they're fossilized relics of the early universe where density fluctuations left behind pockets of near-nothingness. Gas here is exceptionally sparse and often too hot to collapse easily, making star formation a cosmic uphill battle. For a halo to birth a galaxy in such a wasteland, timing is everything. Those that formed early during the universe's cooler, denser youth might have snagged enough gas before the void fully expanded, like grabbing supplies before a store closed forever. Latecomers like DR7 arrived after the void's gas had thinned and warmed, leaving them eternally starved. But isolation adds another twist. Without neighboring galaxies to stir the pot, no collisions to compress gas, no mergers to deliver fresh fuel, void halos rely entirely on their own meager resources. Some might exhaust their gas in a single burst of star formation, flaming out quickly like a match struck in a vacuum. Others could be thwarted by their own dark matter. Simulations suggest void halos grow slowly, their gravity too weak to pull in gas efficiently. If their particles are slightly warmer, moving faster than average, they might struggle to cling to gas at all, dooming themselves to darkness. Yet mysteries linger. Why do some void galaxies, like UDG 33, defy expectations by forming sprawling, diffuse stellar disks despite the odds? Could primordial magnetic fields or hidden reservoirs of cold gas play a role? And what of the faint ghost galaxies detected in some voids, dim smudges of stars that shouldn't exist under any model? Each discovery peels back another layer, revealing a universe where even the emptiest corners hold secrets. These phantom halos are more than cosmic oddities. They're extreme experiments in galaxy formation, showing us what happens when gravity works in solitude. By studying them, we're not just probing the shadows, we're testing the very limits of how a universe filled with dark matter builds its luminous structures. And in their silence, they speak volumes. At first glance, our Milky Way seems like a graceful spiral, its arms winding symmetrically around a glowing core. But peer beyond the shining disk, and you'll find its dark matter halo is anything but orderly, twisted, lopsided, and scarred by a history of cosmic violence. Unlike the neat, spherical halos predicted by simulations, ours bulges unevenly, with dense clumps on one side and ghostly streams of stars stretching in chaotic tendrils. It's as if someone took a cosmic hammer to our galaxy's invisible foundation, leaving it permanently dented. The most glaring oddity, the Milky Way's halo is dramatically off-center. While the visible disk spins smoothly, the dark matter halo tilts, its gravitational center slightly offset from the galactic core. This misalignment shouldn't persist. Gravity should have corrected it over billions of years. Yet there it stands, a silent testament to some ancient cataclysm. One leading theory points to a long-ago collision with the dwarf galaxy Gaia Enceladus, whose corpse now orbits inside us as a tangle of stars called the Gaia Sausage. When this intruder slammed into the Milky Way some 8 to 10 billion years ago, it didn't just scatter stars, it may have punched the halo itself askew like a bullet striking a spinning top. But the asymmetry runs deeper. Recent surveys have mapped bizarre substructures, rivers of stars arcing through the halo in configurations no model predicted. The Virgo overdensity, a sprawling cloud of stars looping above the galactic plane, defies explanation, its origin still debated. Meanwhile, the halo's outer edges fray into filaments, some stretching hundreds of thousands of light years, as if the Milky Way is trailing dark matter seaweed. These frayed edges hint at another mystery. Our halo might not have a clean boundary at all, instead fading unevenly into the cosmic void, the clincher. Even the halo's composition is uneven. Certain regions seem packed with rogue stars moving in unison, while others are eerily empty. One provocative study suggests this patchiness comes from dark matter clumps, invisible subhalos that never manage to form galaxies, lurking like shadowy islands in the Milky Way's gravitational sea. If true, these clumps could explain why some telescope surveys detect unexpected stellar motions, as if stars are being tugged by unseen anchors. What does all this chaos mean? For starters, it paints the Milky Way as a cannibal, its asymmetric halo a scrapbook of devoured galaxies. Every warp, every stream is a fossilized record of collisions that shaped our cosmic home. But more crucially, these imperfections challenge the very idea of halos as static structures. If our own backyard is this messy, what other galactic halos defy the textbook molds? The answer could rewrite not just the Milky Way's biography, but the universal story of how dark matter sculpts the cosmos. Earth might be wrapped in an invisible mane, not of strands you can touch, but of dark matter, hairs, theoretical filaments so dense they could act like cosmic roots anchoring unseen particles to our planet. This bizarre concept comes straight from the minds of NASA scientists who calculated that as Earth hurtles through its galactic orbit, it should comb through the diffuse dark matter halo surrounding us, concentrating these elusive particles into ultra-fine streams. Picture running your hand through mist while most slips between your fingers, droplets collect along the hairs of your arm. That's exactly how dark matter might behave, clinging to gravitational follicles around our world. These hypothetical strands aren't just random wisps. According to simulations, they'd form in predictable patterns, some sprouting from Earth's core like upside-down geysers, stretching tens of thousands of kilometers into space before tapering to delicate tips. Others might arc around the planet like celestial vines, bending under the competing pull of the sun and moon's gravity. The thickest roots, where filaments pierce Earth's surface, could harbor dark matter densities a billion times higher than average, creating ghostly hotspots in an otherwise imperceptible field. Yet for all their theoretical elegance, these hairs remain maddeningly elusive. Detecting them is like trying to photograph smoke in a hurricane. Current instruments designed to catch rare dark matter particle collisions in underground labs lack the precision to distinguish a hair's whisper-thin signal from background noise. Even if they could, Earth's motion might be shredding the filaments as fast as they form, leaving only tattered remnants. Some researchers propose hunting for their gravitational shadows, subtle distortions in the orbits of satellites or GPS signals bending around unseen density spikes. Others suggest listening for faint radio waves, theorizing dark matter particles in the hairs could annihilate each other, releasing bursts of detectable energy. The stakes cosmic. If these filaments exist, they'd offer a direct pipeline to study dark matter without waiting for particles to randomly hit a detector. We could map their structure, trace their origins to specific regions of the Milky Way's halo, even test whether dark matter interacts with itself. But until we develop tools sensitive enough to grasp these phantom threads, Earth's dark main remains a tantalizing what if a reminder that the universe's greatest secrets might be hiding in the subtlest of whispers. At the heart of nearly every galaxy, including our Milky Way, lurks a supermassive black hole, a gravitational monster millions to billions of times heavier than our Sun. But here's the cosmic riddle. How do these behemoths grow so large, so fast? The answer might lie in the invisible embrace of their dark matter halos. These vast, shadowy structures don't just cradle galaxies. They could be pulling the strings behind the scenes, orchestrating the feast that fuels their central black holes. Or is it the other way around? Do the black holes themselves shape the halos that surround them? This chicken and egg dilemma is one of the most tantalizing puzzles in modern astrophysics. Take the case of the early universe, where supermassive black holes appeared impossibly soon after the Big Bang. Quasars, luminous disks of gas swirling around these ancient black holes, have been spotted blazing less than 700 million years after cosmic dawn. For black holes to reach billions of solar masses so quickly, they'd need a staggering supply of gas. That's where dark matter halos might step in. The largest halos act like cosmic fishing nets, gravitational traps capable of funneling enormous amounts of gas toward their cores. The denser and more massive the halo, the more efficiently it can corral interstellar material, delivering it straight into the black hole's waiting maw. Simulations show halos with certain shapes slightly flattened or elongated can even direct gas flows like cosmic aqueducts, ensuring a steady diet for their ravenous occupants. But the relationship might not be one-sided. As black holes feast, they unleash torrents of energy, jets of plasma and radiation so powerful they can heat surrounding gas, preventing it from collapsing into new stars. This feedback could alter the very halo that feeds it, creating a self-regulating cycle. Picture a fireplace. The wood gas fuels the flame's black hole, but the heat feedback dries out nearby logs, controlling how fast they burn. Some theorists argue this balancing act explains why we don't see galaxies with disproportionately huge black holes. Halos might literally put their monsters on a diet when they grow too greedy. The plot thickens when we examine galactic collisions. When two galaxies merge, their halos intertwine, funneling gas toward the newly formed center. This cosmic buffet often triggers explosive growth in the central black holes, which then blast out energy, reshaping the halo's gas distribution. The result: a dynamic tug-of-war where halo and black hole co-evolve, each sculpting the other over billions of years. The most extreme examples, like the galaxy cluster Phoenix A, showcase black holes so gluttonous their outbursts carve vast cavities in the surrounding gas, leaving the halo's structure pockmarked with invisible scars. Yet mysteries remain. Why do some galaxies with massive halos, like ultra-diffuse Dragonfly 44, harbor unexpectedly quiet black holes? Could dark matter's properties, whether it's cold, warm, or self-interacting, dictate how efficiently black holes are fed? And what of the rogue black holes detected drifting in intergalactic space, untethered from any visible halo? Each outlier hints at a relationship far more complex than we've imagined, where halos and black holes dance to a tune we're only beginning to hear. One thing's certain: unraveling this cosmic symbiosis won't just reveal how black holes grow, it'll expose the hidden rules governing the universe's most powerful partnerships. Picture a galaxy twirling in the void like a ballerina, its graceful spiral arms tracing elegant arcs through space. Now imagine the invisible dark matter halo surrounding it, an immense shroud stretching 10 times wider than the visible galaxy. Here's the twist. While some of these halos spin in perfect sync with their galaxies, others tumble chaotically, their motion scrambled like a broken gyroscope. This isn't just a cosmic oddity, it's a fundamental clue to how galaxies and their shadowy halos grow together, and why some galaxies flourish while others fizzle out. Take the Andromeda Galaxy, our nearest spiral neighbor. Measurements reveal its halo rotates coherently, like a vast whirlpool swirling in step with the galactic disk. This synchronized spin likely traces back to Andromeda's infancy, when the primordial gas and dark matter that birthed it shared the same angular momentum, a cosmic inheritance preserved over billions of years. But contrast that with the halo around Galaxy NGC 218, which spins in a jumbled mess, its dark matter churning in conflicting directions. The difference, violence. NGC 218's halo bears the scars of a brutal past, its original spin disrupted by a gang of smaller halos that crashed into it like unruly toddlers knocking over a spinning top. Spin matters more than you might think. A smoothly rotating halo acts like a gravitational flywheel, stabilizing the gas clouds inside it. As these clouds collapse to form stars, the halo's steady spin helps organize them into neat, flat disks, the kind we see in spiral galaxies like our Milky Way. But in halos with scrambled spins, gas arrives at the galactic center in chaotic bursts, spurting out in all directions. The result, elliptical galaxies, blob-like and starved of the raw materials needed to birth new stars. It's the difference between pouring water into a spinning bucket where it spreads evenly versus splashing it into a still one where it splatters unpredictably. The real head-scratcher comes when we peer at ultra-diffuse galaxies like Dragonfly 44. Despite floating in a massive, fast-spinning halo, this ghostly galaxy barely formed any stars at all. Why didn't its halo spin translate into stellar fireworks? The answer might lie in timing. If the halo rotated too quickly early on, its centrifugal force could have flung gas outward before it had a chance to clump into stars, like a salad spinner tossing away dressing before it can soak into the greens. Then there's the dark matter wildcard. What if the particles themselves carry intrinsic spin like tiny cosmic tops? Some theorists suggest certain dark matter candidates, like actions, could collectively generate large-scale rotation patterns in halos, adding another layer of complexity to the puzzle. Others propose that magnetic fields woven through halos like invisible spiderwebs might talk dark matter into alignment over eons. The more we study these invisible whirlpools, the clearer it becomes halo spin isn't just a footnote in galaxy formation. It's a hidden conductor orchestrating the fate of galaxies with the silent sway of gravity. And as telescopes map the rotation of ever more distant halos, we're uncovering a universe where even the faintest twists in the dark can shape the destiny of the light. Deep in the heart of our Milky Way, astronomers have stumbled upon a strange glow, a persistent excess of gamma rays radiating from the galactic center like a distant beacon. This unexplained signal, first spotted by NASA's Fermi Space Telescope, crackles with energy that defies conventional astrophysics, too intense to be explained by spinning neutron stars or colliding cosmic rays, yet too diffuse to match any known celestial object. One provocative theory suggests we might be witnessing dark matter's rare calling card, the moment when its particles collide and annihilate in the halo's dense core, transforming into bursts of light. The galactic center is the perfect hunting ground for such signals. Here, the Milky Way's dark matter halo reaches its highest density, a gravitational maelstrom where particles would naturally crowd together. According to leading theories, if dark matter consists of weakly interacting massive particles, these ghostly specks could occasionally bump into each other, annihilating in flashes of gamma rays. The Fermi excess aligns eerily well with these predictions, its energy signature matching what some models expect from WIMP collisions. It's like finding a fingerprint at a crime scene where the only possible suspect is an invisible one. But the plot thickens, alternative explanations abound, each twisting the narrative in a new direction. The gamma rays might emanate from a hidden population of pulsars, dead stars spinning like lighthouses too faint to detect individually. Others propose cosmic rays slamming into rogue gas clouds, or even exotic quantum effects near the supermassive black hole Sagittarius A star. The debate grew so heated that researchers divided into camps, one declaring the signal, smoking gun, evidence for dark matter, another dismissing it as astrophysical background noise. Enter the boxy bulge complication. Recent 3D maps of the Milky Way reveal its core isn't smoothly symmetrical as once assumed, but jagged, a shape that could distort gamma-ray emission patterns. If the excess stems from ordinary astrophysics, its glow should follow this asymmetrical structure. Yet preliminary analyses suggest the signal remains stubbornly spherical, clinging to the dark matter halo's expected profile like a shadow refusing to fade. The implications ripple far beyond our galaxy. If annihilation signals are real, they'd confirm not just dark matter's existence, but its particle nature, opening a direct window into physics beyond the standard model. Experiments like the upcoming Cherenkov telescope array aim to settle the debate, scanning the galactic center with unprecedented precision. Until then, the gamma-ray excess remains a tantalizing enigma, a flicker in the dark that could either rewrite cosmology or vanish into the hum of ordinary cosmic static. Quasars should be the ultimate cosmic party, hosts their dazzling brilliance lighting up entire galactic neighborhoods, surrounded by swarms of companion galaxies drawn to their gravitational pull. Yet some of these luminous monsters are caught in bizarre solitude, floating in halos that look almost abandoned. These lonely quasars challenge everything we know about how the universe structures itself. A quasar's light, after all, comes from a supermassive black hole feasting on gas at a frenzied pace. That kind of appetite usually requires a bustling galactic metropolis to sustain it, not a ghost town. So why do some quasars shine like beacons in the void, their halos eerily empty? Take the case of quasar He 0450-2958, a brilliant anomaly floating in a region so sparse astronomers initially thought their telescope had malfunctioned. Most quasars of its luminosity sit at the hearts of galaxy clusters, where thousands of galaxies jostle for space. But this one's halo contains only a handful of faint dwarfs, as if someone turned off the cosmic crowd setting. The disparity is staggering, like finding a skyscraper in the middle of a desert with no roads leading to it. How did this quasar's black hole grow so bright without the usual buffet of nearby galaxies to feed it? One possibility is cosmic robbery. In denser environments, quasars often steal gas from neighbors via gravitational tug-of-wars. But isolated quasars might rely on a slower, more internal fuel supply, perhaps ancient reservoirs of gas that survived from the galaxy's formation, now funneling toward the black hole in a quiet, sustained trickle. Think of it as the difference between a restaurant constantly restocked by delivery trucks versus one running on a decades-old pantry. The latter might still serve meals, but only for as long as its hidden stash holds out. Another twist, these quasars could be interlopers, hurtling through space so fast they've left their galactic entourages behind. Simulations suggest some supermassive black holes get kicked outward during galaxy mergers, ejected at speeds topping thousands of kilometers per second. A quasar born from such a violent exit might carry its accretion disk the glowing ring of doomed gas with it, shining brightly even as its original halo fades into the distance. Picture a firework launched from a moving car, its glow disconnected from the vehicle that spat it out. Then there's the dark matter factor. Perhaps these halos aren't truly empty, just shy on luminous matter. If a quasar's dark matter halo formed in a region where gas was unusually hot or diffuse, it might have struggled to birth many visible galaxies, even as its gravitational heft remained intact. The quasar's black hole could be feeding on scraps, its brilliance a fleeting flare before the darkness reclaims it. The implications stretch far beyond oddball quasars. If empty halos can sustain such extreme objects, our models of galactic ecosystems might need rewiring. Do these outliers represent a rare phase in quasar evolution, or are they evidence of an entirely different formation path? Every lonely quasar we discover forces us to reconsider the delicate balance between light and shadow in the universe and the invisible hands that shape it. Somewhere beyond the stars we see a cosmic heavyweight lurks, an invisible titan so massive its gravity tugs at entire galaxies, including our own. This is the Great Attractor, a mysterious concentration of mass dragging the Milky Way and its neighbors toward it at over 600 kilometers per second. Yet despite its enormous influence, we've barely glimpsed its face. Thick curtains of interstellar dust in the Milky Way's disk obscure our view, leaving astronomers to piece together its profile through indirect clues. And the most startling revelation, the Great Attractor might be just the visible tip of a far larger structure, a dark matter halo of staggering proportions, its full scale still eluding our measurements. Picture the local group, our galactic neighborhood, as a leaf floating down a river. The river's current is the Great Attractor's pull, guiding our motion through the cosmos. But what's generating that current? Visible galaxies like Norma Cluster account for some of the mass, but mathematical models reveal a glaring shortfall. The gravitational torque needed to explain our motion requires at least 10 times more matter than telescopes can spot. That missing bulk almost certainly comes from an extended dark matter halo, a vast shroud enveloping the entire region like an invisible whirlpool. Here's where things get stranger. Recent surveys suggest the Great Attractor might not even be the main event. It could be part of something far larger, the Laniakea supercluster, a filamentary web of galaxies spanning 500 million light-years. Within this structure, dark matter flows in rivers, funneling galaxies toward denser nodes. Our local group is just one of many caught in this cosmic conveyor belt. The Great Attractor's halo, then, might not be a distinct entity but a localized knot in this grander dark matter tapestry. Yet pinning down its true scale remains fraught with challenges. Unlike isolated galaxy clusters where dark matter's gravity cleanly distorts background light, the Great Attractor sits in a crowded kinematic neighborhood. Its gravitational signal gets muddled by overlapping pulls from nearby superclusters and the even more massive Shapley Attractor beyond it. It's like trying to hear a single voice in a stadium. The roar of the crowd drowns out individual shouts. Efforts to map this hidden architecture are pushing telescopes to their limits. Projects like the Dark Energy Survey chart galaxy motions in unprecedented detail, tracing the underlying dark matter skeleton through its gravitational echoes. Already, these maps reveal unexpected substructures, filaments, and voids, suggesting the halo might be lopsided or even merging with another. Each new finding peels back another layer of the mystery, proving that even in our cosmic backyard, the darkest secrets are still waiting to be uncovered. Cosmologists are locked in a battle over numbers, specifically how fast the universe is expanding. On one side, measurements from the cosmic microwave background, the afterglow of the Big Bang, suggest a relatively sedate expansion rate. On the other, observations of nearby stars and galaxies, often using the Hubble Space Telescope, point to a universe ballooning faster than expected. This discrepancy, known as the Hubble tension, has sparked fierce debates. But what if the answer lies not in the stars we see, but in the dark matter halos we don't? The invisible scaffolding of the cosmos might hold the key. Dark matter halos aren't just passive backdrops, their distribution and clumpiness influence how galaxies move, and by extension, how we measure cosmic expansion. Imagine the universe as a loaf of raisin bread baking in an oven. As the dough expands, the raisin's galaxies move apart. But if some regions of the dough are denser due to unevenly mixed ingredients, halos, the raisins won't spread uniformly. Similarly, if vast, unseen structures, superhalos or cosmic voids skew the local distribution of matter, our measurements of the Hubble constant could be thrown off without us realizing it. Some theorists propose that we're living in a local underdensity, a bubble where matter is sparser than the cosmic average. In this scenario, gravity's weaker pull inside the bubble would let galaxies race outward faster, mimicking an accelerated expansion rate. Alternatively, enormous dark matter filaments stretching across billions of light years might be tugging galaxies in ways we haven't accounted for, subtly distorting our cosmic ruler. The problem: these structures would need to be staggeringly large, far bigger than our current maps of the cosmic web predict, to explain the tension. Then there's the halo evolution factor. If dark matter halos grow more efficiently in certain epochs, their gravitational influence could warp space-time in ways that mimic a changing expansion rate. Simulations that tweak halo formation timelines do show variations in the Hubble constant, though none yet resolve the full discrepancy, the real curveball. Some models suggest that the tension isn't a measurement error at all, but a sign that dark matter's properties, its density, interaction strength, or even its response to dark energy, shift over cosmic time. This isn't just academic quibbling. If halos are masking unseen cosmic structures, it means our entire framework for measuring the universe's age and fate might need recalibrating. Or worse, if the tension stems from something more fundamental, like new physics in the dark sector, we could be on the verge of rewriting cosmology itself. Every new galaxy survey and dark matter map brings us closer to an answer, but for now, the Hubble tension remains a glaring reminder. The universe's darkest corners might be pulling the strings, and we're only starting to sense the tug. Galaxy clusters are the titans of the cosmos, colossal cities of hundreds or even thousands of galaxies bound together in a single, sprawling metropolis. Take the Coma cluster, a behemoth 300 million light-years away, where galaxies zip past one another at thousands of kilometers per second. What keeps these galactic skyscrapers from flying apart? The answer lies in the dark matter halo enveloping the entire cluster, an invisible scaffold of gravity strong enough to reign in even the most rebellious galaxies. Yet when scientists peer toward the cluster's outer edges, they uncover something unsettling. The halos there refuse to match the tidy profile simulations predict, as if dark matter itself forgets the rules at the fringes. The mismatch starts with mass. According to cold dark matter models, galaxy clusters should follow a universal density profile, steep and concentrated toward the center, then smoothly tapering off in the outskirts. But observations of clusters like Coma tell a different story. At their outer limits, dark matter's gravitational grip seems weaker than it should be, with mass measurements falling short of predictions by as much as 50%. It's as if the cosmic glue holding these clusters together starts thinning out prematurely, like tape losing its stickiness at the edges. Some researchers suspect this missing outskirts mass could hint at dark matter interacting with itself in ways we don't yet understand. Perhaps particles colliding or scattering beyond the cluster's core, redistributing energy and puffing up the outer halo. Another clue comes from the chaotic environments where clusters collide. When astronomers study systems like the Bullet cluster, they find dark matter halos plowing through one another with minimal resistance, but the gas between galaxies, a hot, glowing plasma, gets left behind in turbulent wakes. This stark separation confirms dark matter's ghostly nature, yet it also raises questions. If halos are truly collisionless, why do their outskirts seem fluffier than simulations allow? One provocative idea points to cosmic expansion. As the universe grows, dark matter at the edges of clusters might stretch like taffy, diluting its density as it's pulled into the void. Simulations that account for this large-scale tidal stripping show halos with shallower outer profiles closer to what we observe, but the plot thickens when we examine the cluster Able 2283, whose outer halo bends background light so dramatically it creates a gravitational mirage, multiple, warped images of a single distant galaxy. This extreme lensing reveals a halo far more massive at its edges than standard models predict, the opposite of the coma discrepancy. Suddenly, the question isn't just why some halos are underweight at the fringes, but why others defy expectations by becoming unexpectedly hefty. Could there be two populations of clusters, each shaped by different histories of collisions, mergers, or dark matter physics? The implications ripple across cosmology. If dark matter halos at cluster edges don't behave as we thought, it could skew measurements of the universe's total mass, alter our understanding of galaxy formation timelines, even reshape the cosmic web itself. Some theorists are now exploring radical alternatives like fuzzy dark matter, particles so lightweight they behave more like waves, creating halos with inherently softer edges. Others wonder if the answer lies in the interplay between dark matter and dark energy, with the latter's repulsive force subtly eroding halos from the outside in. Every new cluster mapped adds another piece to the puzzle, and with next-generation telescopes like the Vera Rubin Observatory set to scan thousands more, we're on the verge of uncovering whether these mismatches are cosmic exceptions or evidence that dark matter's rulebook needs rewriting. One thing's certain, the glue holding the universe's grandest structures together is far more complex and far more mysterious than we ever imagined. Simulations of dark matter halos predict a menagerie of smaller structures, subhalos, the cosmic equivalents of moonlets circling a planet. These dense knots of dark matter should pepper every galactic halo, remnants of smaller halos swallowed during the galaxy's growth. Yet when astronomers scour the skies for their glowing counterparts, dwarf galaxies clinging to these gravitational anchors, they find a ghost town. Countless subhalos appear to float empty, devoid of stars or gas, like invisible islands adrift in an invisible sea. Are these phantom substructures real or just glitches in our cosmic simulations? The answer could redefine how galaxies assemble and whether dark matter is stranger than we thought. Take the Milky Way. Our galaxy's halo should, by all accounts, host hundreds of subhalos massive enough to birth dwarf galaxies, yet we've spotted barely 30. This discrepancy isn't just a counting exercise, it hints at a fundamental gap in our understanding of how dark matter clumps. Some subhalos might simply be too small to collect enough gas for star formation, their gravitational wells too shallow to trap the raw materials of light. Others could have formed in the early universe's colder, denser pockets, where dark matter piled up efficiently but ordinary matter lagged behind, leaving gravitational pits with nothing to fill them. Yet the plot twists when we examine ultra-faint dwarfs like Segway 1, a wisp of stars orbiting the Milky Way. Its dark matter subhalo is so dense, stars within it whip around at dizzying speeds far faster than the visible mass alone could explain. If subhalos like this exist, why don't more of them show even a flicker of starlight? One provocative theory suggests that subhalos might not be entirely dark. They could harbor failed stars, brown dwarfs, or rogue planets too dim for our telescopes to detect. Alternatively, their dark matter might be warmer than predicted, zipping through space just fast enough to resist gathering gas, yet slow enough to cling together gravitationally. The stakes escalate when we peer beyond our galaxy. In simulations of galaxy clusters like Virgo, subhalos outnumber visible satellite galaxies by a factor of 10. Some of these ghosts even exhibit gravitational lensing effects, bending the light of background objects, confirming their mass despite their invisibility. It's as if the universe sketched an elaborate blueprint for galactic neighborhoods, then forgot to build half the houses, the most tantalizing possibility. These phantom subhalos aren't flaws in our models, but signposts to dark matter's true nature. If dark matter particles interact weakly with themselves, scattering like billiard balls in the crowded cores of halos, they might puff up subhalos, making them more resistant to disruption during galactic collisions. But the greatest mystery lies in the outliers. A handful of observed dwarf galaxies, like Triangulum 2, sit in subhalos far less massive than simulations predict. If these mismatches are real, they could point to a cosmos where dark matter's clustering behavior isn't uniform, where some halos are dense knots, others wispy filaments, all shaped by forces we've yet to discover. The more we probe these invisible realms, the clearer it becomes. The universe's dark architecture is far messier, far more dynamic than any simulation has yet captured. And until we reconcile the phantoms with the light, our map of the cosmos remains half-drawn, its darkest corners still waiting to be revealed. Where does a galaxy's dark matter halo actually end? It sounds like a simple question until you realize these invisible structures don't come with neat edges like planetary atmospheres or city limits. Instead, they fade gradually, their density thinning into the cosmic web like ink dispersing in water. But here's the controversy. While simulations predict a relatively sharp boundary where halos dissolve into intergalactic filaments, real-world observations suggest a far messier transition, as if the universe itself can't decide where one structure stops and another begins. Take the Milky Way's own halo. According to high-resolution simulations, its outer edge should taper off predictably, like a campfire's glow dimming with distance. Yet studies of stars in our galactic outskirts reveal something stranger: patches of unexpected density, sudden drop-offs, and even tendrils stretching far beyond where models say the halo should end. One theory suggests these frayed edges are cosmic scars, remnants of smaller galaxies torn apart by our gravity, their dark matter smeared across the halo like paint on a spinning wheel. But even that doesn't fully explain why some streams of stars orbit in planes that defy the halo's predicted symmetry, as if the invisible scaffolding itself is warped. The mystery deepens when we examine galaxy clusters. These colossal structures, comprised of hundreds of galaxies, should in theory be encased in halos with boundaries so massive they could swallow the Milky Way whole. Yet lensing observations of clusters like Able 1689 show dark matter's grip extending farther than simulations allow, its gravitational influence bleeding into the surrounding cosmic web without a clear cutoff. It's as if the halos refuse to stay contained, their dark tendrils reaching out to intertwine with neighboring filaments like roots in a forest floor. Why the mismatch? One possibility is that dark matter isn't as passive as we assume. If particles interact even faintly, through some unknown force they could carry energy outward, puffing up halos beyond their simulated limits. Alternatively, the cosmic web itself might play a role. Filaments coursing with hot gas and dark matter could feed halos at their edges, creating transitional zones where structure blurs. Imagine a river delta. Where does the river end and the ocean begin? The boundary shifts with every tide, every current. Similarly, halos might breathe in and out, their edges expanding and contracting as they absorb matter from passing filaments or lose it to cosmic expansion. The most tantalizing clue comes from voids, the universe's empty deserts. Here, where galaxies are scarce, dark matter halos are thought to be sparse and isolated. Yet recent surveys hint at faint bridges of matter threading even these barren regions, suggesting halos might not fully disconnect from the cosmic web at all. If confirmed, this would upend our picture of large-scale structure, painting a universe where everything is interconnected by dark matter's intangible threads, from the mightiest cluster to the loneliest void. Resolving this debate isn't just academic. Pinpointing where halos end would refine our measurements of cosmic mass, sharpen predictions for galaxy formation, and even test alternative gravity theories. Until then, these ambiguous edges serve as a humbling reminder. In the dark universe, even the simplest questions like where something stops can defy our best answers. For decades, dark matter halos have been the go-to explanation for the universe's hidden mass, invisible structures whose gravity shapes galaxies and bends light. Yet a rebellious faction of physicists insists we're chasing ghosts. What if dark matter doesn't exist at all? What if gravity itself behaves differently than Einstein predicted? This radical idea, known as modified Newtonian dynamics, offers an elegant alternative. Instead of invoking unseen particles, it tweaks the rules of gravity to explain cosmic oddities. The clash between these two worldviews isn't just academic bickering, it's a battle over the universe's fundamental blueprint. Dark matter's strongest evidence comes from halos' gravitational fingerprints. When we observe galaxy rotation curves, how fast stars orbit galactic centers, they defy Newtonian physics. Stars on the outskirts whirl far quicker than visible matter alone should allow, as if gripped by some unseen hand. Dark matter halos neatly solve this, their invisible mass providing the extra gravitational glue. But proponents counter with a cosmic shortcut. Their modified equations predict those same rotation curves without any dark matter at all, simply by adjusting how gravity weakens over vast distances. It's like realizing a misaligned scale was giving wrong readings, no hidden weight needed, just a recalibration. The debate intensifies where halos seem to falter. Take some ultra-diffuse galaxies, which rotate so slowly their motion contradicts standard dark matter predictions. Handles these gracefully, its equations matching observations without resorting to finicky halo adjustments. Yet stumbles in places where halos shine, like the bullet cluster. When two galaxy clusters collide, their dark matter sails ahead of the visible gas, a separation only possible if mass and light aren't tied together. Struggles to explain this clean divorce without smuggling in some form of unseen matter, blurring its no dark stuff purity. Then there's the cosmic web. Dark matter simulations flawlessly recreate the universe's filamentary structure, with halos seeding galaxies at their intersections. Lacking these gravitational anchors, has no natural mechanism to sculpt the web's intricate patterns. Some theorists attempt grafts like phantom dark matter, mathematical approximations that mimic halos within framework. But these workarounds beg the question: if your modified gravity starts to resemble the thing it's trying to replace, is it still the simpler solution? The truth might lie in the gaps. Certain dwarf galaxies orbit too fast for but too slow for vanilla dark matter models, hinting that both theories might be incomplete. Could dark matter exist and gravity need tweaking? Hybrid theories now explore this middle ground, suggesting halos filled with superfluid dark matter that alters gravity's rules on small scales. It's a messy compromise, but the universe rarely caters to our desire for tidy answers. At its core, this isn't just about equations, it's about how we confront the unknown. Dark matter halos represent a cosmic known unknown, an invisible substance we're racing to detect. By contrast, challenges us to question whether we've misread gravity's playbook entirely. Both demand humility. The first admits we're blind to most of the universe's matter. The second, that we might not even understand its oldest force until a smoking gun emerges, a direct dark matter particle detection, or a galaxy that definitively breaks predictions. The mystery remains wide open. And that's where science thrives, not in certainty, but in the electric tension between competing visions of reality. The fate of dark matter halos hinges on a cosmic tug-of-war between gravity's relentless pull and dark energy's inexorable push. As the universe expands, accelerating under dark energy's influence, these invisible giants face three possible destinies, each more dramatic than the last. Will they dissolve into the void, crushed into oblivion, or outlast the stars themselves? The answer lies in the subtle dance between the universe's most mysterious forces. First, consider evaporation. If dark energy's expansion grows dominant enough, it could stretch halos thin, dispersing their particles across ever-growing volumes until their gravitational bonds snap. Picture a sandcastle at high tide. The structure holds until the water's pull overwhelms it, grain by grain. For halos, this process would unfold over trillions of years, their particles drifting so far apart that galaxies lose their gravitational anchors. Stars would spiral outward, untethered, as the cosmic web unravels into a sea of isolated islands. Some theorists argue this is inevitable, citing models where dark energy's repulsive force eventually exceeds even the strongest halo's grip. Then there's collapse. Contrary to intuition, halos might grow denser as the universe expands. How? In a phenomenon called gravitational cooling. Fast-moving dark matter particles could shed energy through gravitational interactions, sinking deeper into the halo's core over time. Imagine a swirling whirlpool where debris gathers at the center. Dark matter might behave similarly, condensing into ultra-dense nuggets. Simulations suggest these dark matter black holes could form, especially if particles interact weakly with themselves, allowing energy to bleed away. The result, halos that contract into bizarre, glowing cores where particle collisions ignite feeble sparks in an otherwise dark universe. Yet the most haunting possibility is immortality. If dark matter is truly stable and non-interacting, its halos might persist indefinitely, their structures frozen in time like cosmic fossils. Even as galaxies fade and stars burn out, these ghostly frameworks could endure, their gravitational wells intact long after the last light winks out. In this scenario, halos become the universe's final architecture, silent witnesses to a post-stellar era where dark energy has pushed all visible matter beyond the horizon of observation. It's a chilling thought. The universe's grandest structures might outlive everything else, their presence felt only through the faintest gravitational echoes in an otherwise empty cosmos. But here's the twist: dark energy itself might not be forever. Some models suggest its strength could decay or flip side, collapsing the universe in a big crunch. If that happens, halos would face a fiery reunion, merging and compressing as space contracts, their particles drawn together in a final, cataclysmic embrace. Others propose cyclical universes where halos from one epoch seed the next, their hidden patterns imprinting on newborn galaxies like echoes across time. The ultimate fate of dark matter halos isn't just a question of cosmic bookkeeping. It's a window into the deepest laws of physics, a puzzle where gravity, quantum mechanics, and the vacuum of space itself collide. Whether they evaporate, collapse, or stand eternal, these invisible giants hold the blueprints of reality, and their destiny is woven into the fabric of everything we know. From the phantom giants of the cosmic dawn to the eerie plains of satellite galaxies, we've journeyed through 25 of the universe's most perplexing dark matter mysteries, each one peeling back another layer of our cosmic ignorance. These shadowy halos defy everything we thought we knew about gravity, structure, and time itself. The missing satellites that refuse to appear where simulations say they should. The ghostly ultra-diffuse galaxies floating in halos far too massive for their starlight. The ancient quasars blazing impossibly bright in halos that shouldn't have formed so soon after the Big Bang. Every anomaly whispers the same truth. Dark matter isn't just a placeholder in our equations. It's the universe's most cunning architect, weaving invisible scaffolds that bend light, stretch space, and choreograph the dance of galaxies across billions of years. Consider the Bullet Cluster, where colliding halos sailed past each other like ghosts through a wall, proof that dark matter feels gravity, but none of the universe's other forces. Or the Milky Way's lopsided halo, its asymmetry a fossilized record of galactic cannibalism. Even the great attractor's unseen bulk, dragging entire galaxies toward it with the gravity of 100 quadrillion suns, hints at halos so vast they warp the fabric of local space. And who could forget the gamma-ray excess at our galaxy's heart, a flicker that might be dark matter particles annihilating in the halo's dense core. Each mystery isn't just a gap in our knowledge, it's a doorway, the most humbling realization we've barely scratched the surface, with next-generation telescopes like Rubin and Euclid set to map billions of halos, and underground detectors growing more sensitive to potential dark matter particles. We're standing on the brink of revelations that could rewrite physics itself. Maybe the answer lies in actions, sterile neutrinos, or something even stranger. Perhaps dark matter halos hide dimensions we can't perceive or interact through forces we've yet to name. One thing's certain, the universe loves a good puzzle, and these 25 mysteries are its masterpiece. So stay curious. The next breakthrough might be hiding in the spin of a distant halo, the glow of a gamma-ray signal, or even the comments below. Tell us which mystery captivates you most. Because in this grand cosmic detective story, every observer counts, and who knows, the clue that cracks the case might be out there right now, waiting for someone to connect the dots. After all, the universe's greatest secrets don't give themselves up easily, but that's what makes the hunt so thrilling.